Since FLUX.1 came out, I wanted to try to run it on my computer, but the problem is that FLUX.1 is a 12 billion parameter model, not including the 4.5 billion parameter text encoder, and I only have a 6GB laptop GPU. After reading some Hugging Face diffusers documentation, I got it working on my machine, but there are a couple of other things I want to show you. I only needed 3 lines of code to get Flux working on my computer. So the most important one is this line, to enable sequential CPU offloading. What this does is that it loads weights onto the GPU such that only one layer is loaded into the GPU at a time. And what this means is that Flux's parameter count doesn't affect its VRAM usage at all. The biggest layer in Flux has less than 6 million parameters, which is only 12 megabytes of storage, so that can easily fit on a GPU. And the other 2 lines have to do with the VAE decoder. The first one is to enable tiling, and this is useful for images over 1024 by 1024 resolution. What this does is that it takes the input image and then it just runs the VAE over chunks of the image rather than the entire thing at once. And then the second line was to enable slicing, which is kind of like tiling but over a different dimension. Slicing, it makes the VAE run with batch size 1, which is pretty important if you want to increase your efficiency with running Flux. So to run Flux as efficiently possible, you have to increase the batch size. And when you enable the sequential CPU offloading, I found that the transformer actually uses less memory than the decoder. So ideally we want to increase the batch size for the transformer but keep the batch size for the decoder as small as possible. I've done some experiments where I made the batch size, like, not instead of 1, I made it to 2 to try to increase the performance, but it actually stayed the same. And with these 3 lines of code, Flux uses only 2.6 gigabytes of VRAM for a single 1024 by 1024 image. So over here, num images per prompt is 1. The baseline, it only uses 2.6 gigabytes of VRAM. And for 8 images, it only uses 4.8 gigabytes. So I should mention that this memory usage, it only includes allocated tensors. There are some other sources of VRAM that could cause a memory overflow. For example, PyTorch, it has a caching allocator, which takes up like 125 megabytes of storage. And the rest of my system seems to be using 375 megabytes. Over here it says 0.357 gigabytes. Just like doing nothing. So I need like an extra 500 megabytes in addition to the memory that's reported here to get an accurate description of how much my system will use. Okay, running with 1 image, it gives an MFU of 37%. So MFU is just like a description of a model speed where 100% represents just like optimal speed. It represents like the theoretical max speed of a model given its flops as well as the max flops of the hardware. So for a single image, the baseline runs at 37% MFU, which is kind of sad. But for 8 images, the baseline implementation, it uses 62.5% MFU, which is twice as efficient as 1 image, which is why I care a lot about big batch sizes. But I thought that we could do better. 62% doesn't seem like a lot, and 4.8 gigabytes, I thought we could do better than that. So so to get this optimization, I had to do some tweaks into the source code. So let me get to that right now. Alright, so I'm in the transformer flux file, and the main memory optimization was to just delete activations once they stop being used. So delete, alright, over here. So you can see over here, I'm just deleting a bunch of activations, which is kind of, it looks kind of stupid, but what this does is that within a forward call, all of these tensor activations, unless they're explicitly deleted like over here, they're just gonna stay within the GPU VRAM and just hog up the memory for future layers until it goes out of scope. But within this function, it's just gonna be hogging up memory. So by deleting all of these random, well, not random, but deleting all of these activations after they're useful, we can save a lot of memory from this. And then I also had another slight memory optimization, but it was mainly a performance optimization. So I was profiling Flux under N-site systems, and what I found was that there were a lot of random kernels that were slowing down the inference a lot. So the main ones were from ROPE, the rotary positional embedding. This was like 10 kernels, and each of them were pretty, like a little bit slow, but 10 kernels, it's a lot slow. Also, there was some slowness from the normalization, which is that, and then also some other ones from the modulation, which are basically just like multiplying and then adding. So for all of these kernels, the thing to note is that they're all memory bound. So what you can do is this technique called operator fusion is this rope, it takes like 10 kernels to run, but if you can somehow put all of them into one GPU kernel, it'll run at the same speed, but instead of 10 kernels, you have one kernel. And that's what this torch.compile does. It basically just fuses all of this stuff together into one kernel. And over here, you can see I have torch.compile for the normalization as well as the modulation. So I think this sped up inference by like 5% and, well, I mean 15%, and it also saved a bit of memory. But the main boost to my speed was from my matrix multiplication. So let me open this file over here. This data was all collected from just like reading GPU specs as like from the white sheet and stuff. And if you read the white papers, you'll learn that the tensor cores on consumer cards run fastest when you're doing FP16 inputs with FP16 accumulation. So you can see over here, for 3090, if you have FP16 inputs with FP16 accumulate, you have 142 teraflops. But if you have FP16 inputs with FP32 accumulate, then you only have 71. And then the same thing applies for like the 4090 as well. So, and then there's like a fun fact that I learned from doing all of this. It looks like the consumer cards, which are these, they all have like pretty weak tensor cores compared to the enterprise cards. So for example, a 3090, which is like ampere based, if you're doing FP16 with FP32 accumulate, then it uses, a tensor core does 64 multiplies in one clock cycle, but if you're doing an A100 with FP16, like the same inputs, then the same tensor core will do 256 multiplies per clock cycle. So that was kind of interesting to know. And the weird thing, back to my original topic, was that this fast tensor core implementation is not accessible through PyTorch. You only have access to these two. So I was talking to another person who was also optimizing Flux, and he said that he made a repo to just like a PyTorch wrapper around cuBLAS, so we can get access to the FP16 accumulate layers and hopefully get a big speed up. Alright. So using that guy's code, let me bring back to this. Alright, what I essentially did is I replaced all of these, all of the torch linear layers with the FP16 accumulate layers. And when I replace these layers, I get these speedups. So if you have batch size 1, you go from a 32% speedup to a 49% speedup, which is like a 50% speedup increase. That's pretty awesome. And then if you have batch size 8, then before, where you're just using Torch's linear layers, it's 71%. And then after, it's 90%, which is like a 25% speedup. It's not as much. Over here, these this is essentially the same as this. So the only difference is that there's also the guy who made this code, he added an option to do fused GALU activation, and that just sped things up just like a little bit, like 1% for both cases. But the main speed up was replacing the linear layers with the FP16 accumulate layers. Now, this is kind of interesting that the lower batch sizes have higher speedups compared to the higher batch sizes. This is a compute bound thing that we're trying to fix. So since there's more compute on the higher batch sizes, I would expect a bigger speed up. And that's usually the case, but for my GPU, I think it's not, because let me pull up my GPU thing again. I'm using a 3060 laptop GPU. The thing about laptop GPUs, low power maxes. So the equivalent desktop version of this is 170 watts for a 3060. And what that means is that this GPU is pretty limited on my power. If it maxes at power, it's forced to reduce its speed in order to stay under its power limits. And when I'm doing FP16 with FP32 accumulate, it seems to work just fine. It can go to its boost speed, its max speed, but if I run FP16 accumulate, then my GPU has to throttle itself to essentially half speed to stay under its power limit. And when I did extended tests, the FP16 accumulate layer was almost the exact same speed as the FP32 accumulate layers. But I noticed that for short bursts, the FP16 accumulate layer is faster than the FP32, which is why I get speedups. And then the final optimization for performance was converting the decoder to channels last format. I don't have it here, but it's within the diffuser's code. So the reason for this is that tensor cores do convolutions in channels last format, so the decoder is a CNN written PyTorch. But the thing is, PyTorch, the thing about PyTorch CNNs is that it's channels first format by default. And what happens is that you have this channels first format tensor, and then you want to run it through the convolution, but you have to now convert it to channels last, then run the convolution, and then you have to turn the channels last format into channels first. And these like two transposition operations where you're doing from channels first to last and vice versa, that causes unnecessarily, it's just like unnecessarily slow. But before converting the decoder to channels last format, I had to replace its normalization with, normalization. So over here, I have like a custom implementation, and then this is the original implementation. So the reason I had to do this is because Torch's GroupNorm implementation doesn't support channels last format. This one over here, it does. So it can actually leverage the speed up of the channels last format. And the nice thing about this implementation is that it has a fused activation after the normalization by default. So that saves a little bit of speed, but the main speed up is from just like enabling channels last format in the first place. So I was talking about all of these optimizations. There are a lot, but each of them are actually pretty simple to implement. Like this one over here, this is the one that required the most code. If you don't count the like implementing all of the cuBLAS stuff and the CUDA stuff. So these are all simple optimizations, but they gave really good performance increases. So over here you can see, let me see. Okay, so if you have batch size 8, the before optimization it took 4.8 gigabytes, but after it's 2.6 gigabytes. That's almost like half the memory consumption, and it's like it produces the same exact outputs pretty much. And then for monoflops utilization, the transformer is 62%, and then it goes like 40% up to almost 90%, which is crazy. And then the VAE, the decoder, it goes from 52% to 68.65%. That's a 30% speed up. Now, I should say that this transformer MFU is technically wrong because the FP16 accumulate layers is supposed to be twice as fast compared to the FP32. So in reality, like this might actually this should be closer to this should be 45%, but it's a bit confusing for my specific case because the max flops that I can reach using FP16 accumulate for my specific GPU is a bit variable, so I don't really know how to calculate the MFU for my specific thing. So I'll just pretend that this MFU is correct, and I'll just give myself a pat on the back for raising this like 40% over the original implementation. All right. I said that I could run Flux with a single gig of VRAM, so let me show you that. So you have to do some things. You have to disable the memory caching. For PyTorch, this reduces the amount of memory that PyTorch uses. I said it uses like 125 megabytes. I think this reduces it to, like this line, it reduces it to essentially 0. It makes things a bit slower though, so I wouldn't turn it off by default. And then also I need to keep this line commented. This also speeds up things, but uses another 200 megabytes of VRAM. And then I also had to add these 2 lines, which reduces the tile size. So I said that the default tile size for the decoder was 1024, but to run this in under 1 gigabyte of VRAM, I have to reduce this down to 256. So let me run this. Alright, so it's going to start running now. And let me go over here so we can just watch the memory usage. While we're waiting, we can talk about future optimization ideas. So the biggest one I'm looking at is int8 optimization, because I'm running this at FP16, but int8 runs twice as fast on the hardware compared to FP16, which is, that's a pretty big speed up. And I also found some code. It does int8 matrix multiplication, which is good, int8 GALU, which is good, and int8 flash attention even, which that's really promising because that's most of the flops within this model. So that's really promising. And I've also looked into using 2 for sparsity. That's another NVIDIA hardware optimization technique. But I've been having some CUDA errors with the current API, so I'll just leave that for later. Alright, so if you check the memory usage, the peak memory usage was like 0.8 gigabytes, which is pretty amazing considering this is a 1024 by 1024 image being run by Flux, which is a 12 billion parameter model, 16.5 billion parameters if you include the text encoder. And you can see over here, it doesn't even run that slowly. It runs at 50% of optimal, of my optimal speed. And that just shows that if you have an NVIDIA NVIDIA GPU with at least 1 gig of VRAM, you can run Flux. You can run Flux.